So hello everyone, welcome back to the channel. I hope you all are doing great. So we were discussing about our previous year questions of the UPSC Geo-Scientist exam, right? And in that we were discussing about our organic chemistry portion. And in that series already we have discussed 5 of the parts on the channel. So in that 5 parts we have discussed 150 questions. Now this is gonna be the part number 6 in that particular series where the next questions we are gonna discuss. Okay, so if you have not watched the previous parts where around these questions 150 questions have been discussed, I'll provide you with the link to that in the description. You can have a look to that as well. Okay, so let us begin with the solution to this one. So the first question is there on your screen. It says which of the following is the correct sequence for the synthesis of 1-bromo 3-trichloromethyl benzene. So what it represents, this molecule you have to synthesize. At the first position bromine it is present, and meta position to it there is presence of this CCl3 group is present. So this molecule you have to synthesize. So from the given options, let us see. The first option, it says the reaction of toluene with the chlorine in the presence of heat or light. So what it is saying is, if I am taking this toluene molecule, that is CH3, and treating it with the chlorine in the presence of heat or the light conditions if it is taken. So that will do the substitute, basically the hydrogen atoms of this methyl substituent that is present. So you are gonna get us this particular product if the sequence you are following. So bromination is not being done. So this is not your correct answer. Right, now next one, it says reaction of toluene with the chlorine and the Fe. So basically it is saying, so this part I'm writing it over there. So this we are taking is toluene CH3. This is treated with chlorine in the presence of the iron. So this is gonna do the chlorination on the benzene ring. Like CH3 group it is present at the ortho position and as well as at the para position. The chlorination it will be done. So this type of the species you will be getting it. Now further, if you do the bromination of this in the presence of heat or light, so bromination it is done in the heat or the light conditions if it is done. So this is gonna replace the bromine, this hydrogen atoms will be replaced. So CBr3 and at the para position Cl plus its ortho species it will be formed. So this is gonna be the product. So we can see this is not your desired one. So B option is also not the correct answer. Now the option C, if I see, it is saying this reaction of toluene. So this is CH3. This is treated with the chlorine in the presence of light or the heat conditions if it is done. So this will replace the hydrogen atoms of the toluene. So we will be getting a CCl3. So this is in the step number 1. Further, the treatment is done with the bromine in the presence of the iron. So this is gonna do the bromination on the benzene ring, and CCl3 group it is gonna be the electron withdrawing group. So meta position the electrophilic substitution it will be done. So you can see we are reaching up to the desired molecule, which was the 1-bromo 3-trichloromethyl benzene. So this is through the option C. We can say the correct sequence that is given to us we are getting is the correct match. Okay. So C is the correct answer to this particular question. Now let us move upon to the next question, that is this one. It says which of the following, what is the major product when benzene it reacts with the N-propyl chloride in the presence of anhydrous AlCl3. So what it is treating is this benzene species we are having. This they are treating it with N-propyl chloride. So this species, and you are having is AlCl3. So Lewis acid has been added to it. So in the first step, this chlorine molecule that is bearing the lone pair of electrons and this Lewis acid that you are having its vacant orbital, p orbital that is present, this electron density it will be transferred. So you will be getting the generation of the electrophile, basically it will be forming, that is your AlCl4 negative it will be formed. Along with that you will be getting is this 1, 2, 3 a carbocation species it will be formed over here. Now further you can see this carbocation that we have formed, it is your primary carbocation. It can undergo the 1,2 hydride shift to get a more stable carbocation. Right? So from this positions, hydrogen atoms 1 to hydride shift it will be taking, and you will be getting is this secondary carbocation, which is more stable as compared to the primary one. Now this electrophile species that we have generated is gonna go for the attack over the benzene ring. So this benzene ring you are having, and you are treating it with this electrophile. So finally the species you will be getting is this one. This is the molecule that you will be getting. So that you can see it is in the option B that is given to us. So B is the correct answer for this question. Okay. Now the next question we have, that is this one. It says which of the following substrate it undergoes the bromination reaction on the aromatic ring at the fastest rate. So what you have to do is basically on this benzene rings that is present over here, in which of the cases you are going to observe the fastest bromination. So in the bromination reactions, basically your Br positive, that is your electrophile, it is electrophilic substitutions are taking place. Electrophilic substitutions are taking place. So for that, electrophilic substitutions, basically it means that an electron deficient species is going to be attacked by the benzene ring. Okay, so we want such type of the benzene ring which is your nucleophilic, or you can say the maximum electron density in which it is present, that is gonna give the fastest rate. So you can see in the molecule A, if I am seeing to this benzene ring at the ortho positions, you can see just the carbon atoms, and to that the hydrogen atoms have been attached. So this can apply only the inductive effect or the hyperconjugation. These effects only it can be applied over here. So here you can see there will be the plus side or the plus edge effect, it will be applied to the benzene ring. Whereas in the molecule B, if you see, here the nitrogen atom it is present that contains the lone pair of electrons. Now these lone pair of electrons it can be transferred to the benzene ring, which means that the electron density on the benzene ring is getting being increased by the plus M effect over here. Okay. In the molecule C, if I see here, you can see hydrogen atoms it is present. So again, this will be applying the inductive or the hyperconjugation effect only. It will be applied over here. But here the nitrogen atom it is present. So that is gonna apply the being an electron withdrawing group. It will withdraw some amount of the electron density. So as compared to the molecule A, to a lesser extent, this inductive or the hyperconjugation effect it will be applied. Okay. Whereas in the molecule D, this carbonyl species that is present, that is gonna withdraw the electron density from the benzene ring. So minus M effect it is applying and withdrawing the electron density from that. So we can see that the maximum electron density it is in the molecule B, where the plus M effect it is applied by the nitrogen atom that is attached to the aromatic. Okay. So this correct answer will be the option B in this case. I hope the reasoning is clear. Now let us move upon to the next question, that is this one. It says the major product formed in the following reaction sequence. So firstly is this alkene species that is given. This is treated with the H positive. So it will lead to the generation of a carbocation species. So how will that be formed? This electron density you can shift it over here, and this can abstract this particular proton. So at this position, a stable carbocation it will be formed. Okay. Now this is gonna be reacting with your benzene, this toluene species that is given to us. So this toluene species, it is treated with this particular electrophile that we have generated. So this is gonna be reacting, and the substitutions will predict basically reactions you can say that is taking place over here. So at the para position, the major species that will be formed, here will be this methyl group and here will be this tertiary methyl group. So this is the species you will be getting. Now in the next step they have passed is the KMNO4, and in the KMNO4 what basically it is an oxidizing agent, and to the benzene ring the carbon atoms that is attached which bears this hydrogen atom, they gets oxidized to the carboxylic acid. Here in the tertiary butyl group, all are the methyl groups only. The carbon that is attached to the benzene ring, there is no hydrogen atom, so there won't be any effect on this tertiary butyl group. So the final species that we will be getting is, it will be COOH, and here will be this tertiary butyl group you are going. So this is gonna be the final product. Now that I can see, it is in the option B, right? So the correct answer will be the option B for this one. So now let us move on to the next one, that is this question. So it says which of the following compounds will not be formed in the given reaction. Okay. So how is the reaction proceeding over here is, basically you can see at this position the presence of the hydrogen atom we are having, and at this position the hydrogen atom presence also it is there. So any NH2, it is going to abstract the proton from here, and it will this electron density will be shifted, and the Cl group it is going to leave. It will give one of the benzyne species, that is this, like this. And here is this isotopically labeled carbon atom that we are having. So this is one of the case. And in the other case, so this is through the part A you can see, and through the part B if you are following, that any NH2 it is abstracting this particular proton. So this electron density it will be shifted, and this Cl group it will be leaving. So in that case, the benzyne species that you will be getting is this one. Okay, just a second. So this benzyne species we are getting, and here is this isotopically labeled carbon. Right? Now further you can see there is presence of the liquid ammonia has been passed. So in that cases if the reactions you are doing, so NH3, so this can attack either on this particular side or at this particular side. That means at the ortho position or at the meta position of this isotopically labeled carbon, the substitutions you are gonna get like this one, and here will be this meta position, the substitution it will be done. Whereas in this part, that is through the other benzyne species that we have drawn, this NH3 species, this can attack at the meta position, or it will be attacking at the para position to the isotopically labeled carbon atom. So this species we are gonna get, that is not this one, sorry, at the meta position it will be there, this one, and along with that it will be at the para position. So these are the products that we can expect from the given reactions. Now you just have to match the options. So you can see in the option A, it is at the meta position that is being formed during the reaction. So this can be formed, right? In the B molecule, if you can see, it is at the ortho position to it, that is also getting being formed. Next is in the option C, it is at the para position, that is also being formed. So what is not being formed is the option D, that is on the carbon where the isotopically labeled carbon atom was there. This attack of the ammonia it has not taken place over there. So D is the correct answer, which is not the product that is formed in the given reaction. Okay. So now let us move upon to our next question, that is this one. It says the correct sequence of the reaction for accomplishing the following multi-step transformation. Okay, so this transformation we have to bring, again the reaction sequences we are being given to us, we have to predict the correct one. In the first case, if I am following, so first is this benzene ring I am having, its treatment has been done with the CH3Cl, that is your ethyl chloride, and the AlCl3. So basically this will give the formation of the toluene, right? Now in the next step they are treating it with the KMnO4, that is gonna oxidize this, here the benzoic acid you are gonna get. Now in the next step they are treating it with the nitric acid and the H2SO4, so that is basically the nitrating mixture. Now COOH, it is gonna be applying the minus M effect, being an electron withdrawing group. So this will do the substitution at the meta position, right? A COOH, and this meta substituted product you will be getting, but we want is the para substituted product. So that is not gonna happen in this case. Now in the option B, if I am following, that is this benzene ring, it is treated with the nitrating mixture, that is your HNO3 with the H2SO4, right? So it will do the nitration of it. So here the nitro group it will be present. In the next step we are having this CH3Cl and the AlCl3 it is being done. So again nitro group it is gonna apply the minus M effect. So at the meta position the substitution it will be done. So this species you will be getting. Further the KMNO4 treatment it will convert the methyl group to the carboxylic acid. This one. So again the meta substituted product we are getting. So that is not gonna be the correct one. Now we have to form now. Let us see the part number C, that the option C that it is saying. Just a second. So now let us see in the option C. Yes. So this one. In the option C, it is saying that benzene has been first treated with the CH3Cl. That is basically the Friedel-Crafts alkylation is being done in this case. In the part C, the benzene ring, it is treated with CH3Cl with the AlCl3. So chlorination, it will, this toluene, it will be formed. CH3 you will be having. Now in the next step you are treating it with the nitrating mixture, that is HNO3 with the H2SO4. So this is gonna be ortho para directing because the electron donating group attached that, so methyl group. Major product will be the para one due to the less steric hindrance involved in this case. So this product you will be getting. Further it is treated with the KMNO4. So this is gonna oxidize your toluene group, that is COOH, and where your nitro group it will be present. So you can see it is in the option C we are getting this our desired product, that is your para substituted species we are getting. Okay. For the D option also you can check, we won't be getting the correct one. So C is the correct answer for this question. Okay. So now let us move on to the next one, that is this. It says which of the following statements are true in the given reaction. So some reaction has been carried out, different products have been given. So let us see on to the options now. It says 1 and 3 are called as the crossover products. So crossover basically means both of these substrates that are given to us, they are involved during the course of reaction. So in the first molecule you can see here only the methyl substituents are present. So if both the species would have been involved, so in one of the cases methyl will be present and the other species that will be present is the ethyl molecule over there. But here both the methyl substituents are present, so that means it is not your crossover product. So one is not my crossover, that means this statement is the incorrect one, right? Next, it says B's option. It says second and fourth are the crossover products. Second, one methyl and one ethyl species that is present. It is your crossover product. And fourth one, it is saying one again ethyl and the methyl species that is present. So this is my crossover product. No doubt in that. And these are formed by the intermolecular reaction. So that is also the true one. If the same species would have been involved in the reaction, that is called as the intramolecular reaction. Now here the different species are being involved for the formation of the crossover product, so that is called as your intermolecular reaction. So the correct answer will be the option B and this case. Okay. So now let us move on to the next, that is this one. It says now the final product X that is formed in the following reaction, you have to find that. So here you can see again an alkyl halide has been given to us and the Lewis acid has been passed over here. So this is gonna generate the result in the formation of basically a carbocation species. So you will be getting this is 1, 2, 3 propyl bromide we are having. If you are treating it with Al, Br3, so this will give you the primary carbocation first. Right? Now for the rearrangement it is possible 1, 2 hydride shift, that is gonna give you a stable carbocation, that is this one. So this species you will be getting. Now this electrophilic species that you are having, it is treated with the nitrobenzene. So now we know that the nitrobenzene species that you have, it is highly electron withdrawing group, and due to that your benzene ring it is highly electron deficient in the nature, right? Electron deficient in the nature. Now, if the ring is electron deficient in the nature, how will it be going for the reaction towards an electrophile? Because opposite species have to attract one another, which means the nucleophile will be interacting with the electrophile. Now, already the ring is electron deficient, so it is not able to attack over the another electrophilic species. I hope this is clear. So now what is gonna happen? You will be seeing that this carbocation that you have formed and in the species while generating the electrophile, your Br negative species that will be present. So this is my electrophile. Now this Br negative it will attack as a nucleophile and will be attacking over this particular electrophile resulting into the formation of this molecule as the final. Okay, so here the bromination it will be not done on the nitrobenzene because of its highly electron deficient nature. So the correct answer will be the option C in this case. Okay, so now let us move on to the next one, that is this. The major products A and B formed in the following reactions. So this is X, you can say. This X1, firstly let us draw it into the chair conformation. That will be like this. Here the OTS group is in the downward direction, that I am drawing it over here. And the OAC group, it is also in the downward direction, that is this one. Okay. So here the OTS group, it is a carbon and the OTS group it is present. This is a sigma bond and the sigma star is in the above direction. Okay. So now you can see OAC group that is present. It is not present in the parallel position to the sigma star where this electron density it can provide. That means no NGP kind of the effect you are gonna observe. So what is gonna happen? Direct SN2 reaction it will be taking place. That is your ACOH species. That is your acetic acid that has been passed using its oxygen atom bearing the linker. It will be attacking over here and this OTS group it is gonna leave. So direct SN2 reaction since it is taking place, so this species you will be getting. Here in the downward direction OAC is present. Now from the above direction this OAC group that is of the acetic acid it has attacked over here. You can draw it into the cyclohexane conformation. Here one of the OAC is in the downward direction and the other one that is in the upward direction. So this is the product that we are gonna get in the molecule X. Could be molecule X if the reaction you are carrying it out. So this is the answer A that we are getting. Okay. So now in the option, this you can say this molecule is the Y1. So this again, let us draw it firstly into the chair conformation so that we can see what type of the reaction. Where the OTS group it is present in the above direction. So we can say that OTS is present over here. Okay, and the OAC group it is present in the downward direction. So this is present in the downward direction like this one. So we can expand this so that we can draw the transition state for this one. So this is O, C double bond O and this CHC group it is present. Now the OTS group is in the above direction, its sigma star will be lying in the downward direction. Okay. So now what can happen? So you can see this sigma star that is of this carbon and the OTS group and this OAC group that you are having, these both are in the parallel position to one another. So this electron density it will be shifted like this, and this oxygen atom electron density it can be easily shifted over here and this carbon and the OTS group it can break from there. So what transition state you will be getting is that is this one, that is from the bottom direction. Here you will be having this oxygen atom that is attached to this carbon atom. Here the methyl group it is present and here the downward direction oxygen and here this double bond it will be formed. This one is gonna carry the positive charge. So this is the transition state that we are gonna get. Now in the next step your ACOH that is present. So here what type of the mechanism that you are observing is SNGP mechanism it is being obeyed over here. Now this nucleophilic species that we are having, it can attack either on this particular site or it can attack on this particular site. Either of the sites attack it is possible. So if same product you will be getting in both the cases, that is your racemic mixture you will be getting So like this the species it will be formed. It will be in the downward direction, OAC group, and the other one that has attacked it is in the above direction. So this is your diaxial species you are getting, and along with that you will be getting is this one that is in the downward direction it is taking place. So where the equatorial side, both these groups it will be present like this. So OAC, these two species you will be getting. So you can draw it into the cyclohexane. So that means both the OAC groups, one is in the upward direction and other one that is in the lower direction we are getting. Okay. So here the NGP effect, through that we are seeing again the trans species has been formed over here. So this is the product B in this case. So in both the cases you can see that is through the X and the Y molecules. The products A and B that we are getting is the same only. That is the trans product we are getting, that is in the option D that is given to us. Okay. Mechanism in both the cases it was different because of the alignment of the groups that are attached to the head. Okay. So now let us move upon to the next question, that is this one. Okay. So it says consider the following solvolysis reaction. So for the solvolysis basically it means we have to consider the carbocation formation and its stability. It will be somewhere involved over here. So the extent of the NGP participation of the phenyl group from the lower to the higher, it follows which of the following order. So what basically it is happening is this group it is applying the NGP effect over there and this OTS group it is leaving from there. Okay, and then the reaction further it is further this OTS group when it has left, so a ring will be formed and further this ACOH group it is attacking and you are getting a final product. So what difference it is present as of this Z group? So more amount of the electron density it will be present on the benzene ring, more amount of the NGP effect you will be observing it, right? So we can say more is the electron density, more is the electron density that is equal to the NGP effect. That is maximum effect you are going to observe in that case. Now the Z, it can be your hydrogen, fluorine, Me or the OMe. These are the four groups that are given to us which we have to compare. So if to the benzene ring, the OMe group it is attached, this will apply the plus M effect over there, right? Whereas in this molecule, if only the methyl substituent it will be attached, it can apply the inductive or the hyperconjugation effect, right? Whereas this species, that is the chlorine atom, if it is attached, this is gonna withdraw the electron density from here. So it is gonna apply the minus I or minus M effect. It is basically applying over here, basically decreasing the electron density from the benzene ring. And the next we have taken is this hydrogen atom it is present. So no effect you are gonna observe in this particular substituent case. So the maximum amount of the electron density in the benzene ring it is observed when the OMe group it is attached to it. So maximum NGP effect you are going to observe when OMe substituent it is there, followed by the methyl substituent. Then will be the hydrogen atom which is not going to, either it is not increasing nor it is decreasing the electron density from the benzene ring, and the least will be for the chlorine group, that substituent which is decreasing the electron density over there. Okay, so the correct sequence will be this one that you can see it is in the option D that is given to us. So the correct answer will be D for this one. I hope this one is clear. So now let us move upon to our next one, that is this question. It says consider the following statements regarding the structures of the naphthalene and the biphenyl. Okay. So, so numbering basically has been done in naphthalene and the biphenyls and their bond orders have been compared. So the naphthalene molecule you have, that is this one, like this, it is present, and the numbering in the naphthalene it is done like this: 1, 2, 3, 4, 5, 6, 7, 8, 9, and the 10th one. So this is the numbering you do in the naphthalene, and the other molecule that is given to us, that is your biphenyl. That looks like this. So here two of the rings that you are having. This one is given as the number 1. This is 2, 3, 4, 5 and the 6. Double bonds are placed in this like this one. Okay. Like this. One carbon atlas. So this type of the species is there. Like this here also. This double bonds are also present. Now to distinguish this, the prime substituents are used in this case. This is 3 dash, 4 dash, 5 dash and the 6 dash. So this is how the numbering it is being done. So thus now by looking at the structures of both of these, you have to compare the bond orders in there. So it says the first statement it is saying is carbon 1 and 2 bond order it is more. So more is the bond order. You can see more is the bond strength or the double bond character it is there, more will be the bond order over there. So it says the carbon between the carbon 1 and 2 bond order is more than between the carbon 2 and 3 in the case of naphthalene. So naphthalene molecule you can see this is the carbon 1 and this is the carbon 2 that we are having. In both of these there is presence of the double bond, whereas between the carbon 2 and the carbon 3 there is a presence of the single bond character. So that is what it is saying and the statement is the true one. Okay. Next statement it says that the carbon 2 and 3 bond order it is more and carbon 1 and 2 bond order than the naphthalene. So that means the reverse scenario it is saying this one is false statement. Okay. Moving upon to the next statement that says the carbon 1 and carbon 2 bond order is more than the carbon 2 and 3 bond order in the biphenyl. So you have to compare the carbon 1 and 2. So 1 and 2 is this one. Either you can consider 1 and 2 or 1 dash or 2 dash. Similar environment it is there. So I think 1 and 2 they are having more bond order than the 2 and 3. So this is not the scenario. You can see 1 and the 2 single bond and then 2 and 3 this is your double bond character it is present between them. So 2 and 3 is having the more bond order as compared to the 1 and 2, right? So this statement is the false one. Next statement it says 2 and 3 they have bond order is more than the carbon 1 and 2 bond order in the biphenyls, which is your true statement. So you can see 2 and 3 it is having the more of the bond order. So 1 and 2 in the naphthalene and 2 and 3 in the biphenyls they have the more of the bond order. So the correct statements it will be the 1 and 4 that is given in the option, right? So B is the correct answer for this particular question. Now let us move on to the next one, that is this. It says the correct order of the increasing acidic strength of the given carboxylic acid. So carboxylic acids have been given. So we have to draw the structures of this. 4-acetyl benzoic acid. This is one of the structures you are having. Here the COOH and here is C double bond O and this CH. This is 4-acetyl benzoic acid. Next species it is 4-cyanobenzoic acid. So here COOH and here will be this cyanide. Next is 4-hydroxybenzoic acid. So that means here is this OH group that is present and here is this COOH. Next is benzene 1,4-dicarboxylic acid. That is this one, COOH and the COO. So the major difference is of these substituents that are present over here. This one. We have to see which of the following species it is gonna stabilize the conjugate base that will be formed after the loss of this acidic hydrogen from the benzoic acids. So here maximum stability of the conjugate base you have to basically see the one that is going to provide the maximum stability, it is going to be of the highest acidic strength, right? So here you can see in the given options I can see the one in which the dicarboxylic acid it is present, it is going to be of the maximum acidic strength, right? So here you will be seeing that the dicarboxylic acid, wherever acids when you are seeing these are of the maximum acidic strength, followed by your cyano group which is gonna apply the minus M effect. No doubt this is also gonna apply the minus M effect, but here it will be applied to a more extent. So cyanide group it will be there, followed by your acetyl group which is again applying the minus M effect only, and the least will be in the case of the hydroxy group, where hydroxy group it is applying the plus M effect to the benzene ring, that is it is destabilizing the conjugate base that will be formed. Okay, both of these they will be applying the minus M. So the correct sequence is this one, that my dicarboxylic followed by the cyano followed by the acetyl group, and the least is the hydroxy, that is in the option B we are seeing here. So the correct answer is the option B in this case, right? So now let us move upon to the next one, that is this question you are having. So you have to find the major product X and Y for the given reaction. So you can see here the benzene ring it is present, and along with that a 5-membered ring where the 2 of the nitrogen atoms are present. Treatment it is done with the 1 molar HCl. So basically with the HCl treatment is being done, that is your acidic species. You just have to locate the position where the protonation will be done through the acid. Okay, the site where the maximum electron density you will be observing, that particular site it will be protonated, right? So here I can see this guanidinium type of the base it is given to us. So here the nitrogen atom that is containing this lone pair of electron density, it can be shifted over here, which can be eventually shifted to this particular nitrogen center. That means that this nitrogen center it is now having the maximum amount of the electron density. So this one is gonna be protonated. So this site you will be having is the protonation. Okay. So the final product will be this one, that you can see it is in the option B. It is given this nitrogen center is protonated, and also you can see it is in the option D. You are seeing that this nitrogen center it is protonated. So A and C you can eliminate from the here, right? A and C it will be cancelled out. So among B and D, for the next question we can take it. So here this endole kind of the species you are having, or the pyridine ring along with this 5-membered ring pyrrole species that is present. So here in the pyridine ring, this nitrogen atom that we are having, it is your localized lone pair of electrons that is present. Whereas in this 5-membered ring, you can see this nitrogen atom, it is involved in the conjugation that is responsible for the aromaticity of the ring. So this is basically your delocalized one. Delocalized electron density. So the one in which we are having the localized electron pairs it is present, that means it can provide the more amount of the electron density to the acidic medium, so it will be protonated easily as compared to the delocalized lone pair of electrons. So at the 6-membered ring that is containing the nitrogen center, that will be protonated, that is in the option B. You can see this nitrogen center it is be protonated. In the option B it is this 5-membered ring it has been protonated, so that won't be there from there. So the correct answer will be the option B in this case. Okay, I hope this is clear. So just based upon the electron density acid base reaction only it is being done. Okay. Now let us move upon to the next one, that is this question you are having. It says the correct decreasing order of reactivity towards the ionization under the acidic condition of the following compounds. So these species you are having, and in the acidic medium the treatment has been done. So what basically it is they are doing is this OTS group that you are having, it can easily leave from the medium, and due to that you will be getting is the formation of the carbocations over there. So in the first molecule the carbocation formed will be like this nitrogen center it is present, and this ring it is present. The carbocation it is formed over here. In the second molecule, when this OTS group it is leaving, you are gonna get as this type of the species, that is this one. Here this bond it will be present, and the positive charge it will be present over there. Here is this methyl. And in the third case when it is leaving, we can say this type of the species that will be formed. Here the methyl substituent, this one is present as it is, and at this position the positive charge it will be generated. So based upon the stability of the carbocation, if I see, you can see where the presence of the nitrogen atom it is there in the first and the second molecule, that is this carbocation which is being formed. this nitrogen atom, it can apply the plus M effect. So in the first molecule, if I see, I cannot apply this plus M effect. Reason being, this will go against your Brett's rule. Brett's rule. So this double bond, it cannot be formed over here. So that means least stability it will be there in this particular case. Okay. Next one molecule, if I am seeing this carbocation species that has been formed, it can be easily stabilized by this nitrogen atom. Whereas in the molecule third, if you will be seeing, this nitrogen atom, it is present far apart. And this hydrogen atoms only it is present which can apply the inductive or the hyperconjugation effect only to stabilize my carbocation. So maximum stability I can see it is in the molecule second that is being formed. So second one is gonna have the maximum rate, followed by the third one, and the least one rate you will be observing in the first molecule, that is because of the Brett's rule. Double bond it cannot be formed at the bridged position, that is sp2 hybridization we cannot have it. So that means nitrogen atom it is not going to provide any kind of the stability to the carbocation. Rather it is going to apply the, being the electron withdrawing group, it will withdraw the electron density and it is going to destabilize your carbocation by applying its minus R effect. Okay. Whereas in the third case also you can see this nitrogen atom of the ring, it can apply the minus I effect, and inductive effect is the distance dependent. So it is farther apart from the carbocation. So lesser amount of the inductive effect it is of this nitrogen atom being applied over there. So we can say that the maximum stability it will be due to the plus M effect of the second one. In the second case of this nitrogen atom, then the less amount of the minus I effect that you are observing of the nitrogen atom in the molecule third, and the first case that is there where the nitrogen atom it is closest to the carbocation. So maximum amount of the impact minus I effect it is being applied. So least order of reactivity will be in the this one. So according to me the correct answer is this one, that is your option B, right? So this is the correct answer to this question. So now let us move upon to the next question, that is this one. This is from your aromaticity topic. So the reactions have been given. You have to find where the products you are getting are the aromatic in the nature. So in the first molecule if I am seeing, so how many this double bonds are present, you can count it. 1, 2, 3, 4, 5, and the 6 you are having. If you treat it with the lithium that is your alkali metal, it is gonna provide the electron density to it. So that is gonna form the anionic species. So that means you will be having the 7 pi electron bonds it will be present, pi electron bonds it is present. So that means you have 14 electrons it is present. So for the aromaticity, the molecule should be cyclic, planar, and it should follow the Huckel's rule. So by the 14 pi electron species, you can see that it is having the 4 into the 3 plus 2, that is Huckel's rule it is being followed over. 14 pi electrons are being formed. So that means the in the molecule number 1, if the reaction is carried out, so we will be getting is the aromatic species, right? Now in the molecule, the reaction B if I see, or the second reaction if I am seeing, this tub-shaped molecule we are having. So here you are initially having 4 of the double bonds are present in this. If you treat it with the sodium metal just like the lithium metal only, it is gonna give the Na positive and the electron density will be provided. So one pi bond it will be increased over here, or the anionic species that will be formed. So in total 5 pi bonds we will be having. So which represents the 10 pi electrons that will be present. So again you can see 4 2s are 8 plus 2. So 10 pi electrons will be present. That means the Huckel's rule is again getting being obeyed over here. So this molecule that you will be getting is again your aromatic species only. Right? In the third reaction if I am seeing, so this is treated with the methyl lithium. So here you can see in the with the help of methyl lithium, it can act as an acid base reaction or it can give, so methyl negative can abstract this particular proton, And also the second molecule of it that you are having, it can abstract this particular proton, which will give you a dianionic species that is gonna look like this one. So here you will be getting this. This species is another 5-membered ring we are having. Here the negative charge it will be present and this pi bond. Here this and here the negative charge and here this pi bond it will be present. So just count the number of the pi bonds. You will be getting 1, 2, 3, 4 and the 5. That means total 10 pi electrons again we are getting. So this is again your aromatic species you are getting. Right? In the fourth reaction, if I see here again the lithium metal it is given, so lithium is gonna give the lithium positive and along with that your electron density it will be provided. So here this type of the dianionic species it will be formed over here. So you can see again you are having a 6 pi electron, so that is your aromatic species. So in all the four of the given reactions you can see you are getting is the aromatic species only. That means the correct answer is the option D, where it is given that 1, 2, 3 and 4 all of the reactions are giving us the aromatic species. Okay, so D is the correct answer to this particular question. So now the next question that we have, this one we are having. So this question it says that match the pair of compounds from the column 1 with the stereochemical relation with each other from the column 2 and select the correct answer using the code that is given to us. So here you can see column 1 and 2 you are having. Here the relationship between this four of the different molecules that is N, N, O and P is given. We have to predict what is the stereochemical relationship between them, that whether they are identical, gas, stereomers or they are not enantiomers. So here you can see different types of the projections are given to us. One is in the Sohor's projection you are having or Newman projection. So let us bring all of the given four molecules in only single projection, that is the Fisher projection we can bring it so that we can make the comparison easily. So here the N molecule that is given to us, it is in the Sohor's projection that is like this. We are having, this is CHO, this is Br you are having, here is hydrogen, here the hydrogen methyl and the above one is your Br. Now to draw it into the Fisher projection, we have to bring this into the eclipse conformation. That means around the first carbon atom, that is this one, we can do the 180 degrees rotation. So after the 180 degrees rotation, you will be getting is the eclipse conformation. Like this you will be having. So here we will be having the presence of hydrogen, it will shift over here. Methyl will be going over here and this is Br. This is 180 degree inversion we have done at this particular carbon center. At the back carbon, the conformation it is remaining the same. So this is the one. Right. Now we can draw it into the Fisher projection, that is this one. So two of the chiral center, the front one that is present, it is drawn in the below direction. Here the Br it is present. On the right side we have the presence of the hydrogen and the left side is this methyl group. Right? And that other carbon atom, here the right side bromine, here the hydrogen and here you have this CHO group it is present. Right? So this is the conformation that we are having for the N molecule. Right? Now we have to draw for the N1. So from the either from the Newman projection only you can draw the Fisher one, or you can firstly draw it into the Sohor's and then do the convert it into the Fisher one. So we will be firstly drawing it into the Sohor's, that is this staggered conformation. Again it is given to us. Here the bromine it is present, here you have is methyl, here the hydrogen atom. At the back center you have here is CHO, here the hydrogen and this is the Br group we are having there. Again do the 180 degrees rotation around this carbon center to bring it into the eclipse conformation. We will be getting this, let me change the color. So we will be getting as this one, here the CHO, hydrogen and the Br it will be present. Here this hydrogen it will shift over here, methyl over here and this is gonna be Br. Now into the soft this Fisher projection we can have it. Here will be bromine, hydrogen, this methyl group and this is CHO you will be having, and the hydrogen, and this is your Br. So this is your molecule N you are having. So M and N we have drawn it, right? So just let us copy it and we can paste it. So now the N, this O molecule is already given into the Fisher projection only, so no need for the conversion of that. Now the P molecule we have to draw it. Then all the four collectively we will be making the comparison between them. Right now for the P molecule, again now this is given into the wedge dash, you can draw it into the sawhorse and have the eclipse conformation of it, and then the sawhorse, this from the sawhorse you can draw the Fisher projection of it. So I'm drawing firstly its sawhorse projection, that is going to be looking like this. Here the Br, methyl, here Br, hydrogen. Sorry. On the right side is this hydrogen because the wedge position it is present. So here you will be having this is hydrogen, and the left side this is the Br. And here you have the CHO. On the right side it is your hydrogen, and the left side is this Br. Right, again do the 180 degrees rotation. You will be getting this eclipse conformation, Br, hydrogen, this methyl group it will be coming, and at this position you will be having like the CHO, here is Br, and this is your hydrogen. Now in the Fisher we will be having this CHO, Br, hydrogen, and the above other carbon center, this is methyl, hydrogen, and this is Br. So this is the molecule P that we are gonna have. Okay, so this is all the four P molecules that we are having. So now let us just draw all of the four and see the relationship between them. So this is the P molecule already we are having. The M and N we can draw it over here. At the M position we are having this Br, and this is CHO, Br we are having hydrogen, and at this position the Br it is present, here is hydrogen and this methyl. This is your molecule N we were having, and the other one that is the N molecule we have drawn is Br, hydrogen, and the CHO. We are having this Br, hydrogen, and this CHO group that is present over here. And the other center is, here is this methyl group you are having, here is this hydrogen, and here is this Br group you are having. Br opposite ends, methyl and CHO are on the opposite sides. So this is the one we are having. So this is the molecule N we are having. So they are saying the first thing is relation between this M and N molecule you have to find it out. So M molecule is CHO, this is Br, hydrogen, and this is, we can do the 180 degree this conformation around this, we can do this rotation so that methyl group you can bring it onto the vertical line. Here the methyl group, here the Br it will be present, and here you will be having this hydrogen atom. So this is the molecule N you are having, and for the N molecule also around this carbon center you can do the rotations so that CHO it comes in the vertical line. We will be having here is CHO, where this at this position your Br will be present, and here is this hydrogen atom. On the other carbon center also this rotation it can be done so that methyl group it comes into the vertical line. Here your methyl group it will be coming, Br will be shifted over here, and here will be this hydrogen atom. So this is the molecule M we are having, and this is the molecule N. You can see around this carbon center, this we are reflecting is like the mirror images. But here you can see on this carbon center, these both are having the same stereochemistry. That means these are not the mirror images. These are not the mirror images. So that means these are my diastereomers. At one of the carbon center, the stereochemistry is changed, but on the other one, it is the same only. That means these two are diastereomers, which represents that the A relation that is between the M and N, it is gonna have the code that is 2, which is representing the diastereomers. So from this only you can have the answer over here. You can see A under the 2, it is only given in the option A. Rest all others, it is 3, 1 and 3 it is given. The correct answer is option A from here. The rest of the molecules also, since we have drawn it, you can check the confirmations around that as well. You will be getting this. Okay. So A is the correct answer to this particular question. Now let us move on to the next one, that is this. It says which one of the following it has an achiral stereoisomers. Okay. Among these given four, if you will be checking this, that is 1,2-diabromocyclobutane, you will be seeing that can exist as two form. That is both the Br group can be present on the wedge position, that is on the same side, or they will be present on the opposite. That is, one is at the wedge, other one is at the dash position. So you can see that it's cis conformation that we are having. This possesses a plane of symmetry in it. So due to the presence of the plane of symmetry in it, its isomer, it is achiral. That is the cis isomer of it. It is achiral in the nature. The trans one, there is no plane of symmetry. For the other rest of the three molecules also, when you will be checking it, you will be not getting any of the stereoisomer, which is your optically inactive or achiral in the nature. It is a molecule D only you will be getting, that there is plane of symmetry that is present in the molecule, that is the cis conformation of it. Okay, so D is gonna be the correct answer to this particular question. Okay, now let us move on to the next one. That is this. We have to find this the structure which resonate with the RZ36-dimethyl cyclooctane as its IUPAC name is. So the name is given to us. You have to predict the correct structure over here. So Z conformation, we say that when both the hal substituents are present around the double bond is on the same side, right? And R conformation, that is clockwise rotation, it should be there, having the least priority group at the dash position. Yes. So around the carbon number, this A molecule that is given to us, you can see around the alkene, if I check the conformation, this is high priority group on this carbon center, and this one is going to be of the lower priority. Here the other substituent will be the hydrogen atom, and this is 1, this will be 2. So that means around this carbon center, the conformation is the Z conformation only. Next is around in the B molecule. Firstly, let us try to eliminate it through the EZ conformation only. Around the molecule B, if we see, here the higher priority groups, this will be 1, this will be B2, here it will be 1, and this one, hydrogen, will be on this side, that is true. So both of these are on the opposite side, so it will be having the E conformation. That means this is not gonna be the answer for this. For the C molecule also, if you will be seeing, here it is the 1, this is gonna be of the lower priority, this is 1 and this is 2. So both of the higher priority groups are on the same side, so it will be having the Z conformation. That means this can be the option. Next is in the D also, if you will be seeing, it is 1 and here it will be 1. So both of the higher priority are on the opposite side, so this is E. That means this option is also eliminated from here. So using the EZ you have eliminated it. Now answer will be from the A and C only. So check the configuration around the chiral center, that is this one. Here at the fourth position, that is at the dash conformation, is the presence of the hydrogen atom. So we have to give it the numbering now. So the least priority group is the fourth one. This one will be third. This one will be the first. This one will be the second. So first to second to third, it is going in the anti-clockwise direction. That means we are having this the S configuration around this. That means this is not the correct answer. Now around the C also you can check it. At the dash conformation is the presence of this hydrogen atom. Now to give the numbering, this one is of the highest priority. Using the CIP rules we are doing that, right? So this is 1, 2, 3 and the fourth one. So 1 to 2 to 3, this is going in the clockwise direction. That means we are having this the R configuration around this. So Z and the R configuration is present in the molecule C. So C is the correct answer to this particular question, right? So now let us move upon to the next one. That is this. This folic acid, a major constituent of a bile, it has a structure as shown below. What are the positions labeled 1, 2 and 3, that is of the hydroxyl groups respectively in the chair conformation. Okay. So here this decalin type of the systems are given to us, whether it is in the cis conformation or the trans. Based upon that you have to draw. So these two cyclohexyl rings, firstly if you see this one, this is number 1, this is number 2. Both of them they are in the cis conformation because the methyl group and the hydrogen atom are on the same side. So around this it is a cis conformation. So let us firstly draw this one. This conformation it will be there. This is the cis decalin system. Above one is gonna be the methyl group, and here the hydrogen atom. This is also in the same direction we are having it. Right? Now focus upon the substituents which are attached here. Leaving one of the carbon that is at the junction, after the junction, OH group is present in the dash direction. Dash means the downward position it is present. Right? So here you can see at this particular position, this is the junction, leaving one of the carbon center, this one center you are having. Now here it's dash conformation, that is in the downward direction when we are drawing. This is gonna be the OH position, and here this, it is gonna be the hydrogen atom present over here, right? Next is, you can see the above centers. If you see this again, this type of the decalin, this is third and the fourth ring that is present. So here again this methyl group and this hydrogen atom, they are in this is conformation. This 3 and the 4, these are one is 6 membered and other is 5 membered, right? But both are in this is conformation. Sorry, this trans conformation we are having it, methyl and the hydrogen atom. So you can draw it like this around this carbon center. This is gonna be the 6-membered ring we will be having, 1, 2, 3, 4, 5 and 6. And the other one 5-membered ring, it will be looking like this. Just a second. Just one carbon center it is less. But both of them they are in the trans conformation. That means methyl group it is going in the above direction and the hydrogen atom it is going in the downward direction. So this is how this is, and the trans conformation around the decalins or the fused rings you can draw it. Okay. Now comes for the substituents which are attached to it. So here now on this second ring that we are having, here the OH group, that is the second label as the second one, this is also present in the downward direction. So now this is the fused ring that we were having, leaving one of the carbon center, this center we will be having at this particular position. Here your OH group will be present in the downward direction. This is the one that we will be having, and here this is the hydrogen atom that is present in the downward direction, right? And at this carbon center that is labeled as this third one you are having, on this 6-membered ring that is present after this, leaving one of the carbon center, it is present in the downward direction. That means it is present over there like this one. Now you just have to find us the axial or the equatorial position that we are having over here. Okay. So here you can see around this ring, that is the first one that we are having. Here the H atom that is present, this is in the axial conformation, and this OH group that is present is in the equatorial conformation of it, right? Next is this OH group, when you will be seeing, this one is its equatorial position and this one is its axial conformation we are having, right? And this OH group that is present, so here this one is gonna be the axial conformation. So you can see the first one that was labeled, this is the first OH group, this is your second OH group, and this one is the third OH group you are having. So here we are having is the equatorial, axial and the axial conformations of these labeled OH groups, right? So we are having is equatorial, axial and the axial, that is the option C we are having. Equatorial, axial and the axial one, right? So the correct answer will be the option C in this case. I hope so. This how we have drawn it into the chair conformation, it is clear to you, right? Now let us move upon to the next question, that is this one. It is saying that in which of the following compounds the anti-conformer it is more stable than the gauge conformer? So generally when we are drawing the Newman's projection, we say that the staggered conformation it is more stable as compared to the eclipsed one, because there will be no strain in that. The distortional strain it will be absent in the staggered conformation. Now the staggered conformation, further you can see that it is of the two of the type. We can have the NT and we can have the gauge conformation. In the NT conformation, the substituents are present at an angle of 180 degrees to one another, and in the gauge they are at an angle of the 60 degrees to the one another. So if you are having so various factors basically they exist which describes the stability between these two staggered conformations. In this, OH molecules are present. So that means this ethylene glycol molecule that you are having. If you draw the projection in this case, you will be getting something like this. This is the staggered conformation, and here if you place this OH groups that are present at the gauge conformation to the one another, you can observe there is presence of this hydrogen bonding in them. So that means in the ethylene glycol molecule, your gauge conformation it is more stable as compared to the NP, right? Next molecule if you see, that is the difluoroethane that we are having. For this also, if you will be drawing the Newman projection, you will be getting like this. Okay. Here if you keep the substituents, that is your fluorine atom over here, rest are these. And in this case, again the gauge conformation will be more stable. The reason for that it lies into the sigma-sigma star interactions that you are having. So here the back carbon, this carbon fluorine bond that is present, its sigma star will be present somewhere around this one. So here this carbon hydrogen bond that is present, it can provide the electron density to give this carbon and the sigma star bond that is present, sigma star orbital that is present. So this electron density can be present. So due to the sigma-sigma star interaction, this gauge conformation again it is more stable as compared to the NT one. Okay. The reason for this is this one, because if you are having this fluorine atom at the NT position, then not that much amount of the sigma-sigma star interactions you will be observing. That means comparatively lesser stability it will be there. Similarly, if you will be seeing in the molecule D, here OH and the ONA group that is present, again you can observe there will be presence of the hydrogen bonding in it. So the gauge conformation again it will be more stable as compared to the NT1. Whereas if you see in the 1,2-dibromoethane, here the NT conformation it is more stable as compared to the gauge one. Reason for that it lies in the steric hindrance of it, like this. Here the sigma-sigma star interaction that is not playing any role. So here you will be keeping this Br group and the Br group are in the NT position to the one another. Here the rest of the substituents, that is your hydrogen atoms you are having there. So here due to the hindrance, the NT conformation it is more stable as compared to the Gauss one. In case of the halogens, it is only in the fluorine case that you are observing the sigma-sigma star interactions and the gauge conformation it is more stable. Also, the electronegativity of the fluorine is very high as compared to the bromine atom, and its size is very less as compared to the bromine. So, steric hindrance factor here it does not play any role, that is keeping it into the gauge conformation, rather the electronegativity factor it dominates over there. But in the case of bromine, the NT is more stable because of its size. Okay. The NT is more stable, it is only in the case that is of the 1,2-dibromoethane. So the correct answer is the option C in this case. Okay. Now let us move on to the next one. That is this. It says we have to find the increasing order of the SN1 solvolysis reactivity in the ethanol of the following substrates. So here you have to remove the living groups and generate the carbocations over here, and just compare the stability of this carbocations. Just giving. Here also the Cl group it is giving and the positive charges be generated. Here instead of this 6-membered ring, here also the 5-membered ring it is present, just like the sulfur and this oxygen case that you are having. That is like this. You are having 1, 2, 3, 4, and this 5-membered ring it is present, and the rest substituent it is present like this. CH3, and here is this positive charge you are having. Okay. So like this it is present. So rest of the cases it is the same. So by mistake it is drawn the 6 member, it is also the 5 member. Now you just have to compare the stability of the carbocation that has been generated. So carbocations we are having is this one, CH with the CH3. Here the positive sign it is present. Here is this thiopene. Here the CH and the CH3 and the positive sign it is present. Rest bonds are remaining like this. Here you are having this nitrogen atom. It is CH and the CH3. Here the positive charge it is present. And here is this oxygen atom. Just a second. Okay. So here is this oxygen atom and CH3, CH. This positive charge it is present like this one. You just have to compare the stability. This 6-membered ring and that is your benzene ring with this CH3 positive. This is gonna be of the least stability. This is least stable one. Reason being it will be resonance stabilized, but here the carbon atoms or the pi bonds are involved in the conjugation that is providing it the stability. Whereas in the other molecules, if you see, here the lone pair of electrons present on these heteroatoms which is present, and then they are gonna stabilize the carbocation like this. This one it is gonna stabilize the carbocation. Here the nitrogen atom it is gonna stabilize the carbocation, and here the oxygen atom will be stabilizing the carbocation. Okay, so the first one molecule, that is the one that is with the benzene, that is gonna be of the least stability we will be having. Right. Now comparing the rest one, you can see here the sulfur atom and this orbitals overlap. It is the 2p 3p overlap we are observing, whereas in the case of nitrogen atom it is your 2p 2p overlap, and for the oxygen atom also it is your 2p and the 2p orbitals are overlapping. That means this 2p 3p overlap is this poor as compared to the 2p 2p overlap. So the next in the order it will be coming is the molecule 2. That is as compared to the one it is more, but as compared to the nitrogen and oxygen this is gonna be of the less stability, right? Because of the poor overlap. Now for the nitrogen and oxygen, if you will be seeing, nitrogen atom electronegativity, if you see, it is lesser one as compared to the oxygen. So nitrogen can easily apply the stability, that is donation of the electron, that is easily possible because of its less electronegativity. So maximum stability you will be seeing in the molecule third one, right? And in between them there will be the molecule 4. So 1, 2, 4 and 3, this is gonna be the order you will be observing. 1, 2, 4 and 3, that is in the option A we are observing, right? So this is the correct answer for this particular question. I hope this one is clear. So now the next question that we have, it is this one. It says that we have to find the number of the SN2 processes involved in the mechanism of the following reaction. So a reaction has been given. We have to see that what is the mechanism and how many times SN2 process has been carried out. So the substrate we are having is this one. That is your pH. Here you have this bond as present. Here the sulfur atom, this double bond it is present, and here is this ethyl. So how is the reaction proceeding? Here the Br2 that is added to it. So firstly this pi electron density that we are having, it will be added to it, leading to the formation of brominium ion, and along with that Br negative it will be leaving. So this species you will be getting. Here the sulfur, here the brominium ion it will be formed, Br positive like this, and here is this methyl substituent that is attached. Let us assume that this Br group it is coming, brominium ion has been formed in the wedge position. Now in the next step, this Br negative that has left in the initial step, it will be coming and attacking over the empty position to it, and this brominium ion it will be opening over here. So here the reaction that is taking place is your SN2. So first time SN2 reaction will be taking place over here. So here the pH, sulfur, this species, here around this the Br groups at empty position we will be having, and here will be this methyl substituents, right? Now in the final product you can see that here this 6-membered ring it has been formed, and that is possible when the sulfur atom that is present. Here this is 1, 2, 3, 4, 5 and 6. So this sulfur atom with its lone pair it is attacking over at this particular site, and the Br negative it is leaving from here. So we have said that this Br it was present at the wedge position. So this one will be at the dash position to it. Now here this SN2 attack it is taking place and this Br it is gonna leave from here. So you will be getting here the formation of the six-membered ring that is gonna look like this one. Here to this sulfur CH2 and this pH group it is attached. And here when the attack has taken place, so here it was 1, 2, 3, 4, 5 and the 6th carbon center. This is the center we are having. So 1 and 6 bond is getting being formed. At the 5th carbon center there is presence of this Br atom at the wedge position, we can say this is present. Br group it is present over here, and this dash position there will be presence of this methyl group you will be having. So this species you have got it. Now in the next step, so here also you can see this reaction that is taking place is going through the SN2 path only. So second time this SN2 attack it will be taking place. Now the heating condition that is given to us. So here this bond, that is this one, it will be breaking in the heating condition. So final species we will be getting is this one. So this is how the complete reaction is taking place. This is your final product. So how many SN2 reactions has taken place? That is the 2. In the first step, this Br addition that was taking place, and second time this ring formation that was involved. So the correct answer it will be the option A, that is 2 times the SN2 reaction is involved in the given cases. Okay. Now let us move on to the next one, that is this. So the major products you have to predict for the given reactions. So firstly we will be drawing it into the jar conformation of it. So this one you are having is the cis-decalin system we are having. So it will be looking like this, the 6-membered ring, and this is my decalin system. And both the hydrogen atoms they are in the above direction it is present like this. Now here the substituent that is at the dash position, this methyl substituent set is present, right? And to the next carbon center, both the OH groups are at the wedge position, which means in the upward direction these are present. So this is the chair conformation of the given substrate. Now this is treated with the species that is my TSCN, and you are having is pyridine. So pyridine, that is your base, it is gonna come and abstract the particular proton from there. Now which of these protons it will be abstracted? That comes the question. So here you will be seeing if this proton we are abstracting, after that this O negative species that will be formed, it will be attacking over this CSCl and this Cl group it is gonna leave. So you will be seeing that OTS group that will be formed after the reaction like this at this position. OTS group as compared to the axial position at the equatorial position it is gonna be more stable. Here the ring that is as it is, right? So OTS group that is at the equatorial position it will be more stable being the bulky one. So this will be the preferred position where the attack that will be taking place. So you can draw it into the other conformation. The options for this it is given on the next slide. Okay, so you can match this. So here you can draw firstly it into the chair conformation or this from the chair conformation to the cyclohexane form we can go it, but these two are in the cis conformation, these were present. Here at the dash position this bulky group, at the wedge these methyl these hydrogens are present. Here the OH was at the wedge, so it will be remaining at the wedge only, and this OTS group also you can see it is in the above direction only, so it will be at the wedge position. So both the OH and the OTS are in the wedge conformation in the given product. Okay, I hope the reasoning is clear that OTS being bulky, it is preferable we add the equatorial position and not the other OH group it has been reacting with the pyridine and the TSCl mixture. Okay, now the next one that is this species if you draw it. Now this is given the trans-decalin system, so you can draw it like this. This is the trans-decalin. Here the above direction we have the methyl, downward direction is this hydrogen atom. So leaving this one carbon atom Br group that is it is present at this particular position, and here leaving one of the carbon atom this Br group that is present in the downward direction. So you can see here the groups that is present it is at the equatorial position and this one is at the axial position we are having. So when the equatorial, this living group, it is at the axial conformation, the attack it takes place over that side. So Na S pH that is added to it. So S with the negative sign that is present will be acting as a nucleophile, and the electron density in the above direction, the sigma star that is present of it, it will be transferred, and this Br group it is gonna leave from here. So we will be getting this as the final product like this. Here this SN2 attack it is taking place. So from the above direction, this SPH group it has attacked, right? And this is the downward direction, this Br group. Further you can draw it into the chair conformation. From the chair conformation to the cyclohexane form we can go it like this. Now you can check the conformations. That downward direction Br it is present, and this above direction this SPH group it is present over here. Right? So this is gonna be your final product. Rest of the substituents, the above side this methyl group and the dash side is this hydrogen atom. So this is gonna be the product Y that you will be getting, and this is the product X that you were getting. So you can match it from the option. So here OH are both are in the wedge direction, right? OH and OTS they both are in the wedge, and here it was that here this SPH they have reacted, that means at the axial position, this equatorial position, the Br that was present, they have treated it with that. This is not your answer. Next is SPH with this Br group and this OH. So B is, I think it is the correct match for the given options. Right. You can see OTS and OH were at the wedge, and here SPH was at the wedge and Br was at the dash position. This is what we are getting it in this particular option. So B is the correct answer to this particular question. Okay. So now let us move on to the next one, that is this. It says the major products X and Y, again you have to predict. So here the reaction that is taking place is called as the nucleophilic reactions that is taking place. It is nucleophilic vinylic substitutions. Vinylic substitutions are taking place. How does this reactions are taking place? The reason for the reactions, nucleophilic reactions over this alkene side is that the presence of this fluorine atoms which is present on both these alkenes, that makes the alkene to be electron deficient in the nature. So nucleophilic attack it can easily take place. This is reacting like this. Here the substitute, this fluorine atoms are getting the substituted like this. So you will be getting is just one of the fluorine atoms have been substituted with the OET group. Rest species are remaining as it is. CF2 and this Cl group. Here also this fluorine you just replace it with the OET group. You have to replace it. So that means we can see it is in the option A we are having, that is the nucleophilic vinylic substitution it has taken place because of the alkene being the electron deficient. This reaction it is visible. Okay. Now moving upon to the next one, that is this. We have to find the relative SN2 reactivity order of the following substrate. So you can see this species have been given SN2, that means nucleophile is coming and this attack is taking place over here, and Br group it is at the same time leaving from the middle. So this depends upon the steric hindrance, and here since the ring size it has different, so percentage S character is gonna decide at which side the reaction is gonna take place at the faster. So first thing that we are seeing is that as we are moving from the 3 to 4 to 5 membered ring and then to the 6 membered ring, the inner bond angle, if you see, this is 60 degrees, this is gonna be 90 degrees and so on. The angle, that is inner angle, it is increasing like this. Inner angle it is increasing. So outward direction, if you will be seeing, here is this substituent, that is the Br group, it is present over here like this. So as we are moving from left to right, that is from the 3 to the 6 membered ring, here you are seeing that inner S character it is increasing, or outside S character it will be decreasing. Outside S character it is decreasing. So that means 6 membered it is gonna have the least amount of the S character, followed by the 5 membered and then the 4 membered, and maximum it is in the 3 membered ring we are observing it. So S character it is decreasing. So this is the order. So as the S character it is decreasing, so the nucleophilic attack it is gonna be at the faster rate. because electronegativity basically it is decreasing, so carbon and the bromine bond it will be easily able to break over there. So we are expecting according to this, as this percentage as character order we are seeing, we expect that the reactivity order it should be that my 6 member it is reacting at a faster rate, followed by the 5 member, then the 4 member, and least will be in the 3 member where the percentage as character it is gonna be the maximum one. So this is the order of your percentage estimate, right? So this is what we are expecting. But actually what happens is that my 6 member ring, it exists into the chair conformation. Like this 6 member ring that we have, it can exist into the chair conformation at the most stable conformation of the given molecule if you consider, where the Br group will be present at the equatorial position. So at the equatorial position, the attack of the nucleophile it is not possible like this. When the living group is at the axial position, it can easily attack. But when it is at the equatorial position, the reaction it becomes difficult. So due to that, there will be decrease in the rate of the reactivities. So the exact order that you observe, instead of the 6 member, the 5 member, it has the maximum order, followed by the 6 member, it comes at the second position. Then you have is the 4 member ring, and the least is the 3 member ring. Just the change in the reactivity order of the 6 and the 5 member ring, it arises due to the chair conformation of the 6 member ring. Okay, so this is the correct order. So you can match the options. That is the 5th member. That is the first one. It is having the maximum one, followed by the fourth one. That is the 6th member. Then the third one. That is the 4 member ring. And the least is in the second one. That is a 3 member ring. So A is the correct answer for the given question. Okay. I hope this one is clear to you. The reasoning for this is also clear. Now let us move on to the next one. So the next question that we have, it is this one. The statements are given to us. We have to predict the correct one. So reaction alkene is given. It is treated with the HX. One of the cases, it is saying that the addition reaction is shown. Then when addition is taking place, you are getting is this substrate. This product you are getting. And if this product that was formed, if this is a substrate and you are doing the elimination, you are getting is the alkene species. Okay. So the first statement says that addition is favored at the low temperature, whereas elimination is favored at the high temperature. This is your true statement. Generally, what we see is that elimination will be taking place when we provided the high temperature conditions, and that is what is given to us. So this statement is the true one. Next is addition is favored at the high temperature, whereas elimination is favored at low temperature. So this is your reverse statement. So this one is not the true one. Next, it says is that at the high temperature, delta G is positive for the addition reaction, whereas delta G is negative for the elimination reaction. So delta G for the to determine the spontaneity of a reaction, we have is delta G is equal to delta H minus of the T delta S. Right? If you see for the addition reaction, so when the addition reaction it is taking place, the entropy of the system it is decreasing, right? Entropy will be decreasing. So if entropy is decreasing, which means we can say delta S, it is gonna be negative. So delta G in that case, it will be equal to delta H minus of the T, and delta S we have assumed it to be the negative only. So negative negative it will become to be the negative delta S. Negative negative will become positive. So this is equal to delta H plus T delta S. This is what we are saying. Now since they are saying at the high temperature condition, so when we are increasing the temperature, so this plus factor it is gonna increase over here. That is gonna give that the delta G value it is gonna be positive. Delta G value it will be positive in this case. So this much statement it is true. Next it is saying is, whereas delta G is negative for the elimination reaction. Now for the elimination reaction, if you see, that is the reverse of the addition reaction when we are doing. So in that case, your entropy of the system it is increasing. You can see from the one of the initial substrate, you are getting two species getting being formed. So entropy value it is increasing. So in that case, delta G value will be equal to delta H minus of the T delta S. So delta S in this case it is positive. That means this overall factor it is gonna be negative only. So at the high temperature if we are taking it, as the temperature it is increasing, overall T delta S value it is increasing. So which means that the negative term is increasing. So overall delta G value it is gonna come to be the negative. So that means for the elimination reaction this is gonna be negative, and for the addition reaction this is gonna be positive. That means this statement is the true one. And the fourth statement it says that at the high temperature your delta G is negative, and the for the addition reaction and the delta G is positive. That is reverse statement they are saying. So this one is your false statement. So the true statement we have to predict, that is your one, and the third one, that is the option A you are observing it. Right? So now let us move on to the next one. That is this question. The major product formed by the E2 and the SN2 of the substrate. So this substrate you are having here, you have to carry out the E2 elimination and you have to carry out the SN2 reaction and find the product species. So when the SN2 it is taking place, so here this sigma star it is present basically. So nucleophile is attacking over here, and this Br group it is gonna leave, and the attack will be from the opposite end. So we will be getting at this position this methyl group it is remaining as it is, and the nucleophile will be attacking it from the dash position. This species that will be there. This nucleophile is the sodium methoxide. So here the at the dash position we will be having is the presence of OMe. So this species it is getting named. We have to find the UPSC name for this. Okay. So here it is. At the wedge position we are having is this methyl group, and at the dash position is this OMe group. So do the numbering and find the stereochemistry. So it is 1, 2, 3, 4, 5 and the sixth number, that is hexane species that is present. At the third position is this methoxy group. Now find the configuration around this. At the dash wedge position there will be presence of this hydrogen atom which is gonna have the least priority. Fourth one, this OMe group it is gonna have the highest priority. The substituted one will be second and this one will be the third one. So we are going is from the 1 to 2 to 3. This is in the anti-clockwise direction, but hydrogen atom is at the wedge position we are having. So this is gonna have the R configuration at this particular position. So at the third center we are having is the R configuration. Right? Now at the fourth center also we have to find it. So let us just draw this again because there is a lot of hotspots over there. So here is this methyl group, and at the dash position here is this OMe group. Here at the dash position will be the presence of this hydrogen atom. So here this is gonna be the fourth one, this is the third one, this is the first, and this one is gonna be the second one. So 1 to 2 to 3, this is in the anti-clockwise direction, so it is gonna have the S configuration. So 3R and the 4S configuration we are having it in the final product. 3S, 3R and the 4S configuration. And the for the elimination also you can check the product that will be formed. Okay, let us carry out the reaction over here. So here it is at the wedge. This one is at the wedge. For the elimination to take place, the species hydrogen and the Br group should be in the anti-periplanar position to one another. So OMe will be coming. It is at the dash position. This hydrogen atom will be abstracted. This electron density will be shifted and this Br group is gonna leave. That means this alkene species we are gonna get. Here the methyl group it will be present in this. So higher priority groups you can see here the hydrogen atom is present. So around this is 1, this is 2, this is 1 on this carbon and this is 2. Higher priority groups are on the opposite side. So this is going to have the E configuration around this. So E and 3R and 4S that is given in the option C. E for this one and 3R and 4S is in the option C. Right? So this is going to be the correct answer. Now let us move on to the next, that is this one. In this we have to find in which of the following elimination reactions your deuterium is not retained in the alkene formed as the major product. Okay. So here the Br group it is present at the wedge position. Here the hydrogen atom it is present at the dash position, whereas deuterium is at the wedge conformation only. For the elimination to take place, they should be in the anti-periplanar. So NaOET will be abstracting this hydrogen atom and not the deuterium atom. So deuterium, it will be retained in the final product, right? So the product that we will be getting it in this case, it is gonna be this one. Here the methyl, and here also this methyl. Here the alkene will be formed, and here this deuterium atom, it is gonna be retained. We have to find in which it is not gonna be retained, right? So tertiary butoxide. So this type of the reaction already we have discussed that due to the strain present in this norborane type of the system, then elimination it takes place over here. So the product that we will be getting is like this. Here the alkene will be present, and here the hydrogen atom and the deuterium, these both will be retained over here. Okay. In the C option, if you will be seeing, this is gonna be leaving from here. Here also you will be seeing that hydrogen atom, if you will be bringing it into the anti-periplanar position, the electron density it will be shifted, and this group it is gonna be. So here also your deuterium atom, it is gonna be retained over here. So the pH group, and here is this hydrogen atom. Whereas in the molecule D, if you are seeing, taking it into this conformation, that is the E conformation, this deuterium atom, it will be abstracted, this electron density will be shifted, and the Br group is gonna leave. That means this type of the alkene species you will be getting. This type of the product you are getting, that is the deuterium is not retained in the option D in this case. Okay, so D will be the correct answer to this particular question. Now, moving upon to the next one, that is this. It says that which of the following statements is correct regarding the given reaction. So, fluorine atom it is given, and the NaOMe base has taken place, and elimination reaction has been carried out. So now fluorine atom that is present over here, it is not your good living group, not a good living group. Reason being, for a living group, you have to satisfy two of the conditions. That is, a living group either should have the presence of the vacant d orbitals in it, or it should have the resonance present in it. Resonance present in it. So that is why you see that your Cl negative, your Br negative, your I negative, they are having the vacant d orbital in them. So they are a very good living group. Also you see the resonance. The second period elements that we are having, like the oxygen atom, you see the OR negative generally we see, or you can say the NH2 negative, we are seeing these are not the good living groups. Reason being, they do not have the vacant d orbitals in them. No vacant d orbitals. So these are not your stable one. So that is why this OR group, it is not a good living group, but you can see that O, when it is in the conjugation, that is OEC type of the group you are having, O negative with the C double bond or CH3, here the electron density can be easily shifted and it is highly stabilized. So this is my good living group. So for the second period elements, there should be presence of the resonance in them. On the other condition is that for a living group to be the good one, it should have the presence of the vacant d orbital in that. So fluorine, both of these conditions, they are not getting being satisfied. So this is not your good living group. So when you are having not a good living group and the elimination reactions you are doing it, so here you get is the Hoffman product you generally get it. Okay, and the Hoffman product basically it means that the less substituted alkenes are formed in it. Less substituted alkenes are formed in it. Okay, so the major product is the option number one, where the less substituted option, this first option, where the less substituted alkene is getting being formed, and this is your Hoffman product you are getting. Alright, so this correct answer will be the option B in this case. That first is major, and this is called as the Hoffman product because it is your less substituted alkene. Had it been the scenario that instead of the bromine, this fluorine, we are having this bromine or iodine as a living group, in that case, this would have been the this zigzag product, and a more substituted alkene, that is the option B, second option would have been formed in that case. But here it is gonna be the first as the major and the Hoffman product it is called. Okay. So moving upon to the next one. The next one we have is this question. It says, which of the following substrates do not form the trimethylamine as one of the products in its Hoffman exhaustive methylation method. So in the exhaustive methylation method, what we generally do is we take the amine species and we treat it with the methylamine, and that results into the formation of the alkene species generally. So for that, what should be the presence, that each of the nitrogen atom, it should have the presence of the hydrogen atom, that when we are treating that particular amine with the methylamide, this hydrogen atom, it can be replaced with the methyl groups, right? So in the given molecules, you can see that in the first molecule, nitrogen atom, it is having the hydrogen atom attached to it. Second also it is having, third also it is having. But in the fourth and fifth molecule, if we observe, here the nitrogen atom, it is attached with the alkyl species only. Here also this one is attached with this alkyl species. No hydrogen atom, it is attached to the nitrogen atom. That means in the fourth and fifth reaction, if you will be seeing, no exhaustive methylation you can carry it out. So that is gonna give you the trimethylamine as one of the products. So fourth and fifth only will not be forming. So this is what we wanted. Do not form the trimethylamine. That is your fourth and the fifth. Okay. So D is the correct answer to this particular question. Right. So that is it for this part now. This was the last question that was to be discussed in this particular part. So I hope all the questions that we have discussed so far, be it in this part or the previous parts that I have uploaded, all the questions are clear to you. But if you still have doubt at any of the questions that we have discussed so far, you can ask me in the comment section. I will surely reply. Okay. And if you have understood the concepts, so make sure you hit the like button for the video and do share it with your friends as well, and do subscribe to the channel as well, so that you can get notification of the upcoming parts of it. Okay, so thank you so much for watching. We'll be meeting you in the next video now with the next parts of it.